Hi, y'all. Mrs. Blasky again. This time we're talking about gas laws part 2, specifically about Dalton's law of partial pressures. And so Dalton's law of partial pressures tells us that no matter how many gases we mix together, the pressure of each of those gases is going to stay separate. And then when we mix those gases together, the pressures will add together to give us the total pressure in the container. So there are two different ways that Dalton's law gets written out. One is just by saying that if we add up all of those pressures of the gases that are inside of the container, we will get the total pressure inside of the container. Another way is to talk about fractions. So basically what the other part of Dalton's law says is that if a gas is a certain fraction of the mixture, it will provide that same fraction of the pressure. So if I have a mixture of gases and 25% of it is oxygen, then oxygen is going to provide 25% of the pressure. In order to do that, we need to know what fraction of that mixture our gas is. And so we solve for this thing called the mole fraction. The symbol for mole fraction is that curvy little x. It is the Greek letter. So we would take the moles of whatever gas we're looking for divided by the total moles of gas in the mixture. And so that mole fraction times my total pressure gives me the pressure of that individual gas. So I could do that. I could take the mole fraction of B times the total pressure to get the pressure of the gas B. I could take the mole fraction of C times the total pressure to get the pressure of C. So these, both of these equations are on your equation sheet. So they are there and available for you to use whenever you need. The biggest thing that happens with Dalton's law of partial pressure is a very specific type of chemical reaction or experiment that we are actually going to do in class. That is collecting a gas via water displacement. So the reason why this is so useful, as you can see from this diagram that I gave you, is when you do a reaction, a chemical reaction that creates a gas, it can be really hard to collect that gas. You have to have a closed container. You need to be able to pump that gas somewhere or fill up a balloon with it or something. And so we have to have it's a little bit more complicated setup than just being able to pour two aqueous solutions together into a beaker. So in this example in your notes, we've got hydrochloric acid reacting with a piece of zinc metal that's going to create hydrogen gas. So we follow that hydrogen gas up here. It's going to create enough pressure that is going to push through this tube. This tube is connected underwater into an inverted beaker or graduate cylinder or something. And then that gas is going to collect in this upside down container. Now, we know that as that bubbles through, we know that we've got hydrogen gas or whatever gas we want to collect in that upturned beaker. We can measure its volume by measuring how much it pushes that water out of that upturned beaker. But as that hydrogen gas traveled through the water that's in this beaker already, it's going to bring some water vapor along with it. So right now, for this particular reaction, we've got hydrogen gas in that beaker plus some water vapor. And so we need to cancel out that water vapor if we just want to know about the hydrogen. So this is a super classic experiment. Like I said, we're going to do this in class and do these types of calculations in lab. But one of the pieces of information, and this always seems to freak people out, and I'm not sure exactly why, is that we need to be able to subtract away the vapor pressure of water. Now, the best part about this is that that vapor pressure of water is going to be given to you. It's going to say in the problem, hey, guess what? The vapor pressure of water at this particular temperature is this pressure. And all you gotta do is subtract it away from the total pressure, because Dalton's law says that this mixture of hydrogen and water vapor equals the total pressure. So in this container, my total pressure is equal to the pressure of the hydrogen gas that I wanted to collect, plus the pressure of that water vapor that sort of came along for the ride. So what we would see in a problem about this would be something like this data. So we would know the volume of gas we collected. We know what temperature we're at. We know what mass of gas went in there, which means we can figure out moles. And it tells us the pressure of water at 22 degrees Celsius. So if I know the total pressure, that's going to be equal to the pressure of whatever I'm trying to find, plus this 19.8 millimeters of mercury, because that is the vapor pressure of water. So this is a problem that shows up all the time on the AP exam. And so we will practice this lots in class, plus we will actually do the lab that goes along with this. But like I said, the most common way to see this in a question, if you look at example 50 real quick, tells us about this reaction that's going on. The oxygen produced was collected by displacement of water, which tells me that's that sort of clue as what reaction is going on at a total pressure of 754 torr. The vapor pressure of water at 22 degrees Celsius is 21 torr. So I know that my total pressure is equal to the pressure of this oxygen gas that I'm trying to collect, plus the pressure of that water vapor that traveled along with my oxygen. So if my total pressure is 754 torr, my pressure of oxygen plus 21 torr is going to equal that. All you gotta do is subtract. So the pressure of the oxygen gas that I actually collected minus any vapor pressure or any vapor that came along with it from the water is 733 torr. So that's the number that we could then plug into Puvnert or plug into any other calculation that we want to do. So we will be practicing these questions together. We'll be doing this in the lab, and I will see you all later. Bye.